Hi, Science 30. I'm going to do a shorter lecture today on the electromagnetic spectrum. So this is sort of part 2 of electromagnetism. I'm going to go from slides 57 today to slides 74. I'm going to talk about wavelength equations and different waves in the electromagnetic spectrum. So this slide on page, slide number 57 is a pretty important one. This shows all the different types of wavelengths in the electromagnetic spectrum. So you can see the visible light spectrum here, Roy G. Bibb, that's where we see. It's a very small portion of the electromagnetic spectrum. Ultraviolet, X-ray, and gamma rays are more energetic than the visible light spectrum. Infrared, radio, and microwaves are lower in energy on the electromagnetic spectrum. This is also in your data booklet, page 3, right? So you have wavelength stuff. I'm going to look at the wavelength formula. So speed of a wave, and c is the speed of a light wave. C equals f times lambda. Okay, so lambda is a Greek letter that indicates wavelength in mathematics. So you have frequency above here, and this is measured in hertz. So you can see as frequency increases, and below is wavelength in meters. So wavelength is longer when frequency is higher, and as when frequency is lower, and as frequency increases, wavelength decreases. So that's a trend that you should understand. Okay, and you have some common examples of things that run based on these different electromagnetic waves. Okay, so EMR, or electromagnetic radiation, is a wave that consists of a changing electric field and a changing magnetic field traveling at right angles to one another. Excuse me. Energy is not sent through vibration like other types of waves. It's sent in packets of photons, so packets of energy. Okay, it originates from accelerating charges, so that's why things like stars produce a lot of really highly energetic waves, because they have really fast-moving ions. Radiation is energy emitted in the form of particles or waves. So when we talk about radiation, that's really what we're talking about. We're talking about streams of ions, and we're talking about streams of electromagnetic waves. Okay, so we're talking, right? So it's not like what you see in comic books or in cartoons where radiation is toxic waste or something like that. It is something that's radioactive is streaming ions and streaming EMR. Okay, so EMR is a transverse wave, meaning that it vibrates in perpendicular to the direction it travels. Okay. One cycle of a wave from crest to crest or trough to trough is a single wavelength, so this is what we're measuring. So a complete cycle of a vibration. The amount of vibrations that happen is the frequency, right? So in one cycle is a wavelength. So that's what we're discussing. We're discussing the length of a repeating oscillation and how frequently that oscillation repeats. So that's your symbol for wavelength. Okay, so you'll see this with frequency, right? So this dot has the lowest frequency, this is medium, and this is the highest frequency. Okay, so it's the number of cycles of a wave per second. So it is how commonly a wave repeats in this case. So higher frequency waves repeat more often, and so that means the wavelength needs to be smaller. Okay, so that's an important relationship that you should understand. Okay, so as wavelength increases, frequency decreases, but as frequency increases, energy increases, because there's more vibrations, there's more repeating oscillations, so that wave has more energy as a result. Okay? So this is your universal wave equation. So speed or velocity of a wave. I'm not going to discuss just general waves. We're going to discuss light waves for the most part, and we use c for that because the speed of light is 3.0 times 10 to the 8th meters per second. So c equals f lambda. So the thing is, with all electromagnetic waves, they all travel the same speed. What differs is how frequently they repeat and how long their wavelength is. Okay, so if I go back to my electromagnetic spectrum, right? So this is why radio waves have less energy than gamma rays, for example, because radio waves have a much longer wavelength, so their frequency is lower, whereas gamma rays have a much higher frequency because the wavelength is very small, so it vibrates really, really, not quickly, but more, there's more oscillations in the same area. Okay, so it repeats much more often, so it vibrates much more. So it's kind of like two students sitting in class. One person can sit still, and the other one fidgets all the time. You're still doing the same thing, but one individual is moving more because they have more energy. Okay, so electromagnetic spectrum, right? So wide band of different types of electromagnetic radiation, ranging from radio waves to gamma rays. So you should understand this relationship. Higher frequency equals shorter wavelength, and that means higher energy. A lower frequency wave has a longer wavelength but less energy. Now here's the deal, is higher frequency radiation is typically a bit more harmful because it has a smaller wavelength. So if it touches our skin, it can penetrate, as it moves through our body, it can penetrate inside our cells. Okay, and that's what can cause mutation. So that's why you do things like wear sunscreen in the summer to protect yourself from ultraviolet radiation. So it can actually break up your DNA and cause mutation. So in your textbook, I'm going to give you just some quick wavelength equations. Page 421, 7 and 8 are good examples. I'm going to leave 8 to you. Example problem 2.4 on page 420 gives you some practice examples as to how to solve this. But this question says an AM radio station broadcasts on a frequency of 960 kilohertz. Calculate the wavelength of this electromagnetic radiation. So 960 kilohertz. Right, is frequency. Okay. And we know that speed is 3.0 times 10 to the 8th meters per second because it's an electromagnetic wave, that's C, and it's asking you to solve for wavelength. Okay. Now this needs to be converted to hertz. Okay. Right, so converted to hertz, right? Kilo equals 1,000, so 960 times 1,000 is 960,000 hertz. Okay. So I can solve for wavelength now. So I'm going to use the equation C equals F lambda. And I know that C over F equals lambda, and that will be my wavelength in meters. Okay, so I have 3.0 times 10 to the 8th meters per second, and then my hertz is 960,000. And that's going to give me lambda, and I'm going to get an answer in meters. Okay. right, so when I solve for that, I get 312.5 meters. Okay, so that's the frequency of the wave. So number 7 on page 421. Sorry, that's the wavelength of the wave. Okay, so if a city block, right, so that's the wavelength of the AM radio wave. If a city block is about 100 meters long, how many city blocks would it take to contain one wavelength? So you would need 3 city blocks, obviously, right? And that's what 8 addresses to. So you can calculate your own height and figure out the frequency of your cell phone wave if you want. Okay, so that's how you would use that equation. It's pretty straightforward, so I'm not going to spend a ton of time looking at C equals F lambda. Right, you can obviously rearrange this cell for frequency as well if you have wavelength. You're always, that C value is always going to be 3.0 times 10 to the 8th meters per second. All right, so let's look at your different types of waves. All right, so radio waves, they are the lowest frequency produced by low frequency vibrations of electrons within electric circuits. They have frequencies less than 3,000 gigahertz, and you can see this on your data booklet. Right, giga is 10 to the 9th, so radio waves will be below this, so long wave radio. But go back to slide 57 too, and you'll see where those lie. Okay, so less than 3.0 times 10 to the 12 hertz used for communications. So a couple things: you could have antennae that transmit or receive electromagnetic energy in the form of radio waves. We always are receiving extremely low frequency radiation, 3 to 300 hertz. This is comes from power lines and household appliances. So we call this background radiation. So unless you're in a completely deaf zone for electromagnetic radiation, like if I'm in the middle of the woods or something, then we always have background radiation that our body is interpreting. We also use MRI. We use radio waves for MRI. So, right, so those big cylinders that maybe you've had an MRI done because you had a brain injury or a concussion. But those big white cylindric beds that you get put in that you might see on movies or television shows, those are MRI machines, and they're using radio waves and creating a magnetic field inside there to create body images. Right, so radio waves cause hydrogen atoms to give off energy, and this energy can create an image. Okay, so that's what radio waves do. So you can get images of soft and hard tissue as a result, and we can locate where brain injuries are. Microwaves are a bit higher on the spectrum, right? So they would be shortwave radio waves. Okay, shortwave radio and microwaves, right? So you can see, right? So cell phones run off microwaves, and so does your microwave, right? So you cook your food with the same radiation that you listen to your friend talk on the cell phone with, or make your TikTok videos with, and stuff like that. So we use microwaves to map storms and weather mapping as well. So this is a microwave image of Hurricane Katrina. So they are electromagnetic radiation with a frequency between 1 gigahertz and 100 gigahertz. Okay, satellite communications, cooking food. Some overlap with radio wave frequency. They have the same functions, but generally transmit more energy than radio waves. So what you do if you bombard food particles with microwaves is you cause the molecules to vibrate, and that changes their nature, and that causes them to be cooked. So you're causing molecular vibrations. Okay, higher frequency microwaves used for telecommunications like cell phones and GPS because it penetrates through weather patterns. Okay, so microwaves, infrared, we observe this as heat, right? So you can see this is an infrared image of an elephant. The ears are a lot cooler because they use that to cool their body. Right, the red indicates a higher concentration of infrared radiation. So electromagnetic radiation with a frequency between 3.0 times 10 to the 11th hertz and 4.3 times 10 to the 14th hertz. So you can see the frequency increasing from the other two. So just below red light, some animals can see into infrared, and we have infrared goggles, right, that we can see. Your television remote works on infrared radiation. We can beam it. So smart devices work on infrared. Okay, so visible light is a very small portion of the electromagnetic spectrum. Right, red, orange, yellow, green, blue, indigo, violet. 4.3 times 10 to the 14th hertz to 7.5 times 10 to the 14th hertz. When you look at the size of the wavelength, so again, the frequency increases again because we're moving up the electromagnetic spectrum. Red wavelengths are about 700 nanometers. Violet wavelengths are about 400 nanometers. Okay, visible light travels as packets of energy called photons. Actually, all of these waves do, but this is the packet of energy that we see. Sometimes they act as particles, sometimes they act as waves. So this is quantum mechanics. It depends on what we're observing. This is called the wave-particle duality of nature. Right, so those packets of light can be absorbed by photosynthetic organisms, right? And we all know this, and we can use that to make energy. So that's how we know very well that it's energy, because electromagnetic radiation is the base of all food chains, right? So producers take electromagnetic radiation and convert it into glucose, and then that glucose is used to make ATP for all metabolic processes in living organisms. Right, so different plants have different colors because they have slightly different pigments in order to be able to absorb slightly different parts of the electromagnetic spectrum. So green's not absorbed, it's reflected, and that's why most plants look green. That's why chloroplasts look green. Okay, so UV, you should know differences in UVA, UVB, and UVC. So ultra means beyond, so we're beyond the light spectrum. Ultraviolet is what gives us sunburns. So it's electromagnetic radiation emitted by very hot objects. So things that can produce their own heat can emit their own light if they're hot enough. So you can see the frequency increases again, and we're looking at even shorter wavelengths, 400 nanometers to 100 nanometers. UVA, ultraviolet radiation, exists from 400 to 315 nanometers. And you can see what happens here: wrinkled skin, possible melanoma. UVB is an even smaller wavelength. And UVC is quite energetic. It is ionizing radiation. So it will destroy matter and turn it into ions. So UVC breaks chemical bonds, causes DNA mutation, and the ozone layer in the stratosphere generally absorbs this. So what ionizing radiation is, it's very energetic particles that can pass through matter and eject atoms and electrons. So they break up matter. And this creates ions, and these ions are called free radicals. And we talked about that in environmental chemistry. Okay, UV also has quite a few uses because it destroys matter. It can sterilize things like bacteria. We use it in forensics to locate bodily fluids. UV is what's used in light-emitting diodes or LED lights. UV is the main type of energy in lasers. UV is what we use in photography. And UV is really essential for creating vitamin D. So we need it, but we don't want too much of it. So UVA, UVB, and UVC, you have different types of sunscreen that absorbs these things. So UVC is absorbed by the ozone layer. UVA is not absorbed by the ozone layer. And the UVA can penetrate deep into the skin. So you can see different types of molecules that can actually screen those in our sunscreens. Avobenzene, zinc oxide, titanium dioxide. So you want to have at least one of those in a sunscreen. UVB rays can cause cancer as well. They're the primary type of radiation that causes sunburns. All right. So again, those are on my slides. Take a look. X-rays, one of the most energetic rays in the electromagnetic spectrum. So 10 to the 18th to 10 to the 21st hertz. What happens is fast-moving electrons strike a metal target. That's where we get X-ray machines, but they're produced by very, very dense celestial objects that have large gravitational energy, which can create very dense hot cores, right? So stars create X-rays. Very powerful form of ionizing radiation. Dealing with gamma rays and X-rays is one of the biggest things that we'll need to deal with space travel. How do we prevent X-rays and gamma rays that are moving all through the universe? How do we prevent them from moving through our own bodies? We can use X-rays, right? An X-ray, right? We use X-ray imagery. We create a stream of particles. It hits a metal, and then as the metal is hit by that stream of particles, it releases X-rays, and those small amount of X-rays move through our body, and then that can make images of hard tissues for us. So this is an image of a person's gut, and you can see that this is the bowels. This is someone whose bowel is severely impacted. So he's literally full of shit. So that's kind of gross, but there you go. Right, so you should understand how an X-ray machine works. Okay. So this is a diagram of how an X-ray machine works. Okay, so X-rays react with photographic film to create light and dark images. So here's the deal. Dense tissues absorb more photons, and they'll absorb more energy as a result, so they appear lighter on an X-ray exposure. X-rays move through less dense tissues, so they appear darker. So X-rays are produced by a high voltage streaming tube. What it'll do is it'll basically create a stream of electrons. They're moving at the speed of light. They hit a metal target. And as the electrons hit that metal target, they displace ions in the metal, and that produces X-rays. And then the X-rays are streamed through your tissue. So you can only have so many X-rays because you're actually exposing yourself to really highly energetic radiation. Okay, so you knock electrons out of your own tissue, and then that creates an image on photographic paper. Okay? Because ionizing radiation is created. So the X-rays cause you to propagate your own radiation, and then that ends up on photographic film. So this is a quasar. Okay, so this is a collapsing black. So this is a collapsing black hole, right? So it's a supernova that's exploded, and it's collapsing into a black hole. And as the gravitational forces are starting to take hold, this creates a stream of really energetic radiation. So there's only a few things in the universe that can create gamma rays, and so quasar is one of them. Okay. So gamma rays are the highest form of electromagnetic radiation, 10 to the 19th hertz. Okay, so radioactive is a term used to describe substances that emit radiation from unstable nuclei, right? So if they are, energized with a high amount of energy from, a nuclear blast or something like that, that will destabilize the atoms, and then they'll release ions, and the ions will emit radiation. So these are emitted spontaneously. We use them in very, very short bursts. We can produce them in machines on Earth in very short bursts to combat cancer growth, but we have to use them very sparingly. Okay, but it's usually really energetic celestial objects that create gamma rays. We're going to talk about stellar evolution and things like that in the next section. So there's an interesting video. If you go to YouTube, Google Vice, the polygon. So this is where the USSR and Kazakhstan used to do their nuclear testing. So this is a person that lives in the polygon, and you can see obviously he has all sorts of mutations on his face. So he's extra gross. He's blind. So about 1 million people that live in this area of Kazakhstan called the polygon. They have gross amounts of DNA mutations because of exposure to radiation. So when nuclear blasts, kind of hit this desert steppe, it ionized all of the bedrock in the soil, and all that soil is now radioactive. So these people who live there are exposed to radiation all the time. So that has grave effects on their DNA. So the Vice episode, like I said, type in Vice the polygon. The episode's called Genetic Passports. So these people who are born in the polygon have a massive amount of genetic mutation. So it's been suggested by governments that people who are born in the polygon have a passport indicating that's where they're from. And they have a high amount of mutation. So obviously there's a human rights issue there. So it's an interesting thing to discuss. But anyway, there's an interesting case study about radiation there. So take a look at that YouTube video. And that's it for this lecture today. I'll talk about astronomy likely later on next week. Anyway, you can do your exposure to radiation assignment now, and there'll be one more lecture until the end of this unit. We will chat with you later.